My name is Jim Zimmerman. I want to welcome you this evening to this very, very special highlight lecture during the 65th IAC here in Toronto. As a matter of our procedure, we're going to have an opportunity at the end of Dr. Sullivan's lecture to take some questions from you. They will be in writing. Our IF staff is holding their hands up now with pieces of paper. I urge you to contact them, signal to them. They'll come over and give you a form to fill out, a piece of paper. Do it during the lecture as early as possible so that we know you have a question and we can try to respond to as many of them as possible afterward. Dr. Kathryn Sullivan is the Undersecretary of Commerce for Oceans and Atmosphere, as well as the Administrator of NOAA in the United States. Dr. Sullivan grew up in the U.S. She studied earth science in California. She received her doctorate in geology in Canada. She also studied in Norway. She participated in several oceanographic expeditions in both, I think, the Atlantic and the Pacific. Many of you know Kathy Sullivan as a NASA astronaut. She flew on 3 space shuttle missions, including the one that deployed the Hubble Space Telescope. She was the very first American woman to walk in space. Kathy came to NOAA. She was actually at NOAA twice during her career thus far. She came in the 90s as the chief scientist and returned about 3 years later, eventually becoming the administrator and undersecretary. She also led a science museum in Ohio and directed a science education policy center in the same state. Earlier this year, Kathy was recognized by Time magazine as one of the 100 most influential people in the world. We are very fortunate tonight to have Kathy Sullivan with us to share her perspective as a lifelong public servant on preserving our beautiful planet, understanding it, and nurturing it. I want to say one other thing about Kathy that some of you may not know. She is not a stranger to the International Astronautical Federation and the International Congress. In fact, Kathy attended her first Congress, I did as well, in 1985 in Stockholm, Sweden. So I want to welcome you back to the IAC, Kathy. And by the way, in 1985, Kathy and I, for the record, were young professionals. I want to welcome you back to the IAC and very much look forward to your lecture.
Thank you, Jim. I flew in space 2 more times after that IAC, so I'm about 69 seconds younger than you. Well, I'm delighted to be with all of you here tonight and applaud IAC for setting this day as an Earth theme and setting the theme of the Congress overall as what the Earth needs from space. I'd like to build on that proposition. The world definitely does need space. It's a timely and true theme. And the facet of this that I would like to focus on is one particular facet. The world needs space to understand the changing planet we live on, and more importantly than just the scientific understanding, to arm us, to arm human societies with the environmental intelligence that we need to help us prepare for, adapt to, and become resilient to the face of these changes. Let me put a couple of facts on the table to illustrate that to you more carefully. We need to make this science matter to the lives of real world people. You've all seen this loop many, many times. It's an extraordinary view that astronauts have from orbit and that our unmanned spacecraft can give us from orbit of our amazing planet. It's just pretty magical. It's swaths of different colors. You get a first impression of a borderless globe, a single closed system, as Sandy Magnus said this morning. You really lose sight of the traces of nations, of political alliances. You don't see exclusive economic zones or the many other boundary lines that we humans like to draw to separate ourselves into different groups. You also become vividly aware of all the different scales on which the dynamic interconnections between our planet's natural systems operate. And as I know you've heard from probably every astronaut that has ever addressed a Congress, every spacefarer is struck by these sights and by, at the same time, a sense of both incredibly immense power and scale of the Earth, but at the same time also a really remarkably fragile, elegant sense of the workings of this planet. And of course, that's a lovely perspective and a very inspirational and motivational one. But back here down on the surface of the planet, human affairs are a lot more complicated than the orbital view suggests. There are such things as political borders, and relationships across them, gosh, sometimes even within them, can be pretty difficult. The point remains that our ability as human beings to continue to use Earth's resources, sustain our planet, and maintain the vitality and the viability of human societies on this planet requires us to find ways to look across and work across those borderlines. It requires us to share openly and widely our knowledge of this Earth and how it works, and the information that we collect every day about its current state of affairs. And it requires us to take collective actions to prepare our societies to withstand and, when possible, prevent the forces of nature that put the health of our communities on our planet at risk. Earth observations play an absolutely indispensable role in helping us achieve these goals. I hardly need to tell this audience of the many encouraging trends we've seen in this arena and our capabilities in recent decades. There's increasing national and international commitment to share data resources openly, freely, and globally so that ultimately all of us can live wisely and well on this planet. Just in the past few weeks, there have been some really notable examples in that regard. In New York last week, United States President Barack Obama announced that the United States is releasing previously restricted global elevation data from NASA's Shuttle Radar Topography mission. These are 30-meter digital elevation data, 3 times more precise than what has been publicly available before, and they will be used worldwide to improve environmental monitoring, climate change research, and quite importantly, the dynamic modeling of the impact of sea level rise on coastal communities. This will be made available initially for Africa through a user-friendly interface at the United States Geological Survey, and then over the course of the next 12 to 18 months for other regions around the world. In just a few days, literally about 6 days, I think, the Japan Meteorological Agency's satellite Himawari 8 will launch, carrying an advanced imager similar to the one that the United States is building for our next geostationary satellite, GOES-R. The spatial and temporal resolution of this sensor is going to make a tremendous stride forward for imaging over the western and central Pacific and improving tropical cyclone forecasting there. Across the pond in the other direction, Europe has successfully launched the Sentinel-1 mission and again made a decision to provide Sentinel-1 data on a free and open access basis to the world's community. And in the United States, of course, and among many nations, the Landsat archive and access to GPS data are improving everyone's capability to georeference and geolocate these valuable data sets. But let's take a closer look at some of the challenges, some of the changes on this planet that put notable challenges in front of us and that are raising every single year the value of Earth observations data. Measured data of our planet tell us we are living in a warming world. We are seeing larger, more frequent, and/or hotter heat waves over most landmass and expect to see that trend continue in the future with a 90 to 100% probability behind that projection. One telling example, just last year, Australia's Bureau of Meteorology had to add a new color to their heat wave charts to handle the scale of temperatures they're now seeing on that continent. Projections tell us we can expect to see more intense hurricanes in some ocean basins, that heavy precipitation will increase over many regions, wet places will get wetter, and dry regions, already dry regions, will get drier, possibly experiencing more intense droughts. The data tell us all about the remarkable pace at which Arctic sea ice cover is continuing to shrink and to thin, and the Northern Hemisphere spring snow cover is continuing to decrease as global mean surface temperature rises. Around the world, the volume of glaciers and sea ice and ice sheets continues to decrease. Sea level rise has risen an average of 8 inches globally in the last several decades and will continue to rise further in the decades ahead. and this will exacerbate the hazards that coastal communities face to coastal storms. That's a problem because humankind is concentrating increasingly in coastal zones. So the human and social and economic vulnerability that results from that simple statement is growing every year. In terms of the planet's intrinsic systems, heat will penetrate further from the surface waters into the deep ocean, quite likely affecting the global circulation patterns that drive our weather and climate system. And we certainly know the ocean is already becoming more acidic and that trend is likely to continue. Many of these trends and many aspects of climate change will persist for many centuries, even if right now today we could cease all CO2 emissions forever. The carbon that has been emitted in past decades is locked in, and the processes that has unleashed will take centuries more to play out. So all of this leads to heightened social vulnerability in a world where the population will increase from the current 7 billion to 9 billion by 2040, and that implies that we will have to double the current food supply globally if we're to at all begin to feed that heightened population. I mentioned that we are increasingly concentrating in coastal zones. It's also a world where last year saw more climate refugees around the globe, some 22 million, than total war-related refugees. The takeaway from all of this, to my mind, is that the familiar patterns of past years, the ones that we've analyzed statistically to project what we can expect in the future, those familiar past patterns are no longer good guides to what the future holds. The more poetic way to say that is the past is no longer prologue. And the more technical way to say that is the statistics are no longer stationary. We are moving into a very different world. So what I would like to touch on a bit tonight are a few facets of that reality. I'd like to focus a bit more on this notion of environmental intelligence as a really critical asset, a critical product that the world needs from space to prepare for this future. Dive in a bit to illustrate a few ways in which space-based assets are contributing to providing this environmental intelligence, and touch then on a couple of the challenges, social, political, and otherwise, that we will have to tackle together to move forward as a space community in helping to meet these challenges. I've used the phrase environmental intelligence a few times now. It's a phrase we use frequently at NOAA. In fact, we consider it essentially our core purpose. The punchline about environmental intelligence is that this is what provides us foresight. Foresight about conditions that have not yet come to exist. Foresight about conditions we need to plan ahead for, think ahead about, consider alternative courses of action in the face of. This ability to look ahead, to think ahead, to analyze alternative courses of actions, something that we know of is of value to us in our everyday, on the simple matter of a weather forecast. But on national scales, it goes to issues like disaster preparedness and evacuation, and on global scales, it goes, in the end, to the absolute viability of our planet. Let's take a couple of closer looks. West Africa experienced severe flooding in both 2007 and 2008. In 2007, the consequences were devastating. Hundreds of thousands of people were displaced. There was essentially no warning that the severe floods would be hitting them. 1 year later, a seasonal climate forecast produced months before the wet season indicated a high risk of heavy rainfall. This naturally raised fears of yet another disaster, and it sparked the international community and the infected nations into action. Working largely through the International Red Cross and Red Crescent societies, scientists from around the world, including NOAA, worked to translate the scientific forecast of the projected precipitation patterns, first into impacts, what would people really experience on the ground, and second, into decision support information that could actually inform more useful, more productive emergency responses. The result in 2008 was, for the first time, an emergency appeal was issued on the basis of a seasonal climate forecast, a forecast that depended critically on satellite data. And so when the floods did come, as forecast, communities were prepared. The response that took 40 days in 2007 and was quite inadequate took just 24 to 48 hours in 2008. And the cost per beneficiary in the affected communities was 2/3 less. So there's one great example of environmental intelligence in action. That seasonal forecast provided the foresight that helped decision makers pre-position relief assets and prepare the population. Environmental intelligence, don't get me wrong, is not simply the stream of ones and zeros that comes down from a satellite. It is that, coupled with in situ measurements, with analysis, with the combined insights gained by decades of investment in Earth system process research and advanced computational modeling. Having environmental intelligence of the quality that we need to make it timely, actionable, and reliable at scales that matter to human society requires us to continually take the pulse of the planet, to measure its state, to measure the energy in the atmosphere, to measure the energy in the oceans, to measure the exchanges between air and sea, between land and air mass. And more importantly, it challenges us, it requires us to transform those data into information and then into knowledge. And it is, in the end, that knowledge that informs and affects decision-making. At NOAA, we make observations every day, literally from the surface of the sun to the bottom of the sea. These observations are produced by a system of systems that are the foundation of our environmental intelligence enterprise and our foresight. How does this come home to roost? Well, there is the example I just gave you in Africa, but there are many, many more really telling incidents of real people and real communities, real businesses, real national questions that are in the real world, not questions you look up an answer to, questions that we as societies have to build answers to. And environmental intelligence is a critical building block in all of this. So for example, in the United States, when a hurricane threatens to make landfall, the pivotal decision point for our emergency management authority is the quality of a forecast on day 4. 85% certainty on day 4, a tight cone projecting where the storm will hit, is what our head of national emergency management uses to decide where to preposition response assets, which regions in his response network to activate, which communities to order evacuations in, which businesses and families and communities to leave untouched and allow to carry on with their everyday business. In our western states right now, and in particular California, environmental intelligence is what is helping farmers know when to plant, when to irrigate, when to harvest, even what to plant now that seasonal outlooks are much more reliable. In India, seasonal outlooks about the prospect of monsoon are allowing that country's government to know when they do and when they need not begin to buy wheat in the open market ahead of the monsoon season, because we now can give them the foresight to know a monsoon will fail. And if the monsoon fails, crop yields will fail. And if the crop yields fail, they're unable to feed their people. So to be able to know that in a timely fashion, when you can still afford to buy wheat on the open market, the prices haven't spiked yet, that's a really significant benefit of having environmental intelligence. Businesses are asking how they can conserve water, how they can ensure a productive and resilient supply chain, how they can keep the communities where they operate resilient in the face of extreme weather and climate events. The larger quest driving all of these questions is that latter one, the quest for resilience. This is a central priority for our agency and an increasingly high priority issue for the United States. And a robust observing system, including space-based assets, is indispensable to achieving this. So let me probe a few more examples of the ways in which we see this in action at NOAA every single day. Hurricane Sandy is one great example, and let me unpack a little bit how NOAA lived this. We're known, of course, largely and sometimes almost exclusively as the United States National Weather Service. That is one of our units. We produced the on-the-spot track forecast that predicted Sandy would take a left hook into the eastern seaboard of the United States, hitting the New York, New Jersey coastline. Those of you who don't live on this continent or in this hemisphere, a hurricane that turns left, a sharp 90 degrees, is extraordinary. It's never the pattern you expect to see. But this time we did. And crucial to being able to gain that insight were measurements of the properties of the atmosphere taken from operational satellites, in particular from our polar orbiting satellites, which provide 90% by volume of the data that feeds numerical weather models. All of the weather forecasts around the globe no matter what nation or entity produced them, fundamentally depend on these sounding data, as they're called, from the armada of polar orbiting satellites that the United States, Japan, Europe, and others operate in partnership to provide this valuable data stream. Geostationary imagery, such as the image you see here, is always on constant watch, both in the Atlantic and in the Pacific, able to both give us the synoptic wide field of view picture you see here and zoom in on the dynamics of the storm itself, again to help sharpen the specific forecast about what will happen in local communities and at a small scale. So satellite data were indispensable to being able to predict this left-hand hook. And this allowed thousands of people to be evacuated out of harm's way. It allowed electric utility crews to be positioned near the hardest hit areas and ready to go to work right after the storm passed. It allowed subway systems in the New York, New Jersey area to move their rail cars to higher ground so they wouldn't be flooded. Countless actions like that taken in advance. It is important to note, and I want to highlight it just one more time, satellite data streams are indispensable to all of this, but they are not the be-all and end-all. They're not sufficient to the task on their own. Sandy preparedness and response took much, much more than satellite observations to prepare for the storm's onslaught and recover. For example, our forecasters up in Boston relied on simple water level gauges along the shore and data from buoys that are moored in nearshore waters to provide wind and water and tide data during the storm. This helped them refine the critical forecasts of how the storm surge would behave and how far up onto the shorelines it would run. We think about hurricanes as wind events, and the news media always covers them as wind events with hair blowing back on the anchors and jackets flapping. But what kills people in a hurricane is not the wind, it's the water. And so being able to refine our predictions, our foresight about how the water will behave is really the central point to protecting people more fully from such storms. Planes and ships were indispensable after the storm passed to surveying the shoreline, assessing the property, literally redrawing the maps, and to allowing commercial vessels and maritime commerce to start again in the ports of New York and New Jersey and up and down the U.S. coast. The recovery from a storm like Sandy compounds and gets worse if the economy that it has just hit remains stalled for days or weeks after the fact. So being able to speed the resumption of commerce is also very critical. Here's another example on the other end of the scale. You know, the thing about water is it boils down to three questions. Do you have too much? Do you have too little? Do you have the right quality? That's really what it boils down to. And in the western United States, as the yellow and orange colors on this map suggest, the current challenge is too little water, and in particular in California, very persistent drought. Satellite data, again, provide some of the indispensable data that is enabling NOAA, working with other United States partners, to provide farmers, ranchers, water managers, and the public with monthly updates about the condition of the drought and whether it's easing or worsening, and seasonal outlooks that give them several months runway, several months foresight about what they need to be thinking about next, what they need to be preparing for next. Again, in situ sensors for stream flows, for soil moisture, for the water equivalent in snowpack are essential not only to calibrating the satellite signals, but to densifying and localizing the information on the ground. So here in this case, the imagers from NOAA's polar absorbing satellites, such as our current NOAA 19 and the SUMI MPP instrument, are absolutely indispensable to this. California is now in the third year of quite a devastating drought, so people out there are critically relying on environmental intelligence. So again, my point here, environmental intelligence is not scientific data from a satellite. It's not just a paper in a journal about how an Earth process works. It is transdisciplinary, and it requires transsectoral teams working hand in glove with farmers, ranchers, water managers, and other decision makers. These human networks bring information providers and users together around the questions that matter in the real world, and they build the trust that's needed for people to undertake high-stakes decisions such as these. Environmental intelligence is the indispensable currency of these networks, and NOAA works to add value to that add data to that value chain at each of the points that I've described. Finally, one international example, and sadly a flowchart of people and players is the best way to illustrate this one. But a group called the Group on Earth Observations, which the United States continues to play a significant role in, has been working for a decade now to forge communities of practice that integrate data streams and observation providers with end users. This nexus of science and applications is actually one of the hallmarks of the Group of Earth Observations. And our agricultural community of practice is one sterling example of this. Their question in this instance was, how can better monitoring and forecasting of crop production contribute to reducing the volatility of food prices in parts of the world where the 4 food staples, maize, corn, rice, are really a network of food security for sometimes quite marginal populations. Satellites are a major component of this initiative because they can provide timely, almost simultaneous global coverage. They provide transparent sharing of satellite data and ground observations across nations in the key crop-producing areas. And they have enabled this GeoGLAM initiative to begin delivering monthly global crop outlooks to the Agricultural Market Information Systems Market Monitor publication that is hosted by the United Nations Food and Agricultural Organization. Monthly outlooks ahead of the on-the-ground appearance of stress or crop failure have played a critical role in helping to reduce crop price vulnerability and increase food security. So again, this initiative roots on satellite data and also roots on the free and open exchange of data among all nations. Today's environmental intelligence, which we all rely on around the globe, is built upon, first and foremost, the system of systems in space and in situ for observations. NOAA, in our work in this arena, touches many, many of these domains. Our Joint Polar Satellite System, which is the next iteration, the next version of our weather satellites, is the backbone of this forecasting enterprise with 3 to 7 day life-saving forecasts and hazardous weather outlooks. They're improving the timeliness, the accuracy, and the utility of these forecasts. Our geostationary satellites, as I mentioned, are important for nowcasting, and the GOES-R satellite that we will launch in early next year will enable far better forecasts and warnings through instruments with higher resolution, twice the resolution on our imager. Faster time coverage will now be able to take 30-second disks, and the first ever geostationary lightning mapper. We continue to work in partnership with our European colleagues and our French partners on the JASON satellite, a radar altimeter to measure sea level rise and other ocean conditions that are both important to global climate forecasting and to operational uses in coastal zone monitoring and forecasting and Navy operations. All of these systems we share freely and openly with our world partners. So again, satellites, yes. In situ sensors, yes. The data systems and the architectures that let us fuse these streams of data, yes. But most importantly, the human talent that focuses on the questions people are facing and looks back at this plethora of observing and data assets and transforms the data into actionable, timely information. So what are a couple of the challenges? One of them is really directly pertinent to this community. I think a central challenge to the space community in the next 2 decades will be to sustain the space segment that is so vital to this system of systems. No exaggeration to say that lives depend on it. We will need the vigor, the creativity, the passion of everyone in this community to develop systems that the global community can afford to sustain, that are robust, that are resilient, and that are reliable. If the frontier challenge of the first 4 decades of the space age was to develop the ever more refined, the ever more sophisticated, the ever more elegant sensor for the ever more interesting science question, I think one of the central challenges for the space community in the next 2 decades will be this one, about space architectures for Earth observation that are robust, resilient, and more affordable, at least for those key observations that are most critical to the global enterprise of environmental intelligence. We are going to need you more than ever, but applying your creativity to a different aspect of the challenge. We're also going to need to continue to work together on the challenge of data, and there are 2 fronts here. There is maintaining the collection of data, but also the challenge of sharing the data. Sampling the globe well enough to do environmental intelligence, measuring it broadly and frequently enough to do that, is a challenge that no country can meet alone. That's why the essential data for environmental intelligence have been treated as global public goods since the inception, since the very earliest days of weather forecasting. From the sharing of barometric readings, from the sharing of balloon data, till nowadays sharing the large data sets that come from our satellites. Open data is a cornerstone of United States policy and NOAA's way of doing business. We believe strongly that it fosters innovation, it creates new industries and job opportunities, that these data as an open innovation platform deliver more social value, but also more economic value, both to the United States and to all the countries of the world than a purely privatized or commercial system would do. We've seen evidence of that in the release of US government weather data, Landsat data, and GPS data, each of which releases have fueled industries valued in the billions every single year. This is why the United States has been such a strong supporter and an advocate of GEO, because this is exactly what GEO orients its work around: to coordinate observing systems, to advance broad open data policies and practices, to foster increased use of Earth observation data information, and to build the capacity to use these data streams, to use this information in every country of the world. At the January Ministerial Summit that we held in Geneva, GEO member countries and participating organizations renewed their commitments to the principle of full and open access to data. We will continue to build on the 10 years of progress we have made in the past, and we are inspired by the results of that first decade. To date, more than 65 million data resources have been shared by the GEO community, including products, files, and images. And some 50 million of those are accessible at no cost or low cost. GEO has also worked to develop a portal for all these data for this global Earth observing system of systems, and you see that figuratively shown here in this slide, which is designed to make it easier for anyone to discover, to search, to understand, to access, and to use these 65 million data resources. The second aspect of the data challenge, of course, is the sheer volume of data itself. Environmental intelligence and Earth observations are certainly prime examples and quintessential big data challenges. The terabytes per day that NOAA, for example, currently produces will soon be terabytes per second in data rates, as Copernicus comes online, for example. And that's not even to take account of the vast stores of data many agencies and countries have in their archives, often in sort of almost unfindable servers, unlabeled archives, cryptic places to try to find it. That might as well be in shoeboxes in our bedroom closets if we expect someone else to be able to use it. So the challenge here is how can we and how must we make these data streams and the metadata needed to make use of them discoverable, searchable, accessible, retrievable, and interoperable across users. This, too, is a central challenge that we're taking on at NOAA, and we're trying something certainly quite different for us in our approach to this. And I suggest the approach in this cartoon, and I apologize, it's like reading an eye chart at your doctor's office to try to read parts of it. But here's the essence of it. We collect or produce 20 terabytes of data per day at NOAA. Our information architecture currently only lets us put 2 terabytes out the door for public consumption. That's the 2 terabytes that propel the United States commercial weather industry and support our international partners, by the way. So billions of dollars of annual revenue are built on only 10% of our data. And we asked ourselves the simple question, suppose we could turn that around. Suppose we could put all 20 accessible quickly in the hands of other users. What different applications might they discover and build based off of those 20 terabytes? We can't solve this problem alone. We know we won't solve the program through public investment in rebuilding our information architecture. So we put out a request for information earlier this year to the venture capital world, to the companies like Amazon and Google and the big aerospace companies that we see here, and said, surely there's another business model out there where the value to be gained by mining, analyzing, and creating value-added products from all these data, that is the business model, and that business model is robust enough that you can co-invest in changing the architecture that we work with. We have been very gratified with the responses that we've gotten so far. Taught us a lot about things we don't know, but gave us a lot of information also to confirm the path ahead and keep us on track. So look for us to put a request for more concrete proposals out sometime in the early part of next year as we work to change our model in a way that unleashes the power of more of our data. I mentioned the continuity of Earth observations, and I just wanted to highlight and visually bring that point home more fully here. We show in this slide just the current sequence of NOAA assets and our European partner assets. Also at the bottom, our Japanese partners with GCOM W1. What I want to highlight to you is if you look in the afternoon orbit, which is the orbit that historically the United States has put a satellite up into to support the global enterprise. Right now we have 5 different assets, 5 different sets of sensors, able to back each other up to make sure we have a robust supply of data from that orbit. But if you look out in the middle and right-hand side of that chart, 2025, 2026, that's not too far off in the future, as all of us know who build space architectures. The stream gets much, much thinner. The system gets more fragile. We will not have the same kind of armada in the 2026, 20 to 30 timeframe. We won't have as many eyes in orbit. So the importance of each set of eyes, the importance of our shared efforts and our collaboration to make sure that we do still continue to take the pulse of the planet from space, from orbit, that is going to rise over the years ahead. We're working very hard in the United States, both NOAA and NASA and our Defense Department, to confront this challenge, to reevaluate and reassess our business models, our architectures, to continue the programs we're working with now so we don't cause a gap in the data streams between now and 2026, but to really push hard to see if there are alternative, more creative, more innovative ways to do this work in the future, to engineer a system of systems that enables greater and easier fusion of sensor data, that optimizes the end-to-end systems from the raw radiance on a satellite sensor to the decision on the other end, to bring in the talent and creativity of the space community to driving these new architectures forward. The challenge questions I ask myself in this arena are typically 2. I keep asking, why can't we have iPhone-class sensors in orbit? A couple $100 a sensor, maybe $1,000 a sensor. What are the barriers to that? What would it take? How might swarm technologies change the equation radically in how we do the environmental intelligence business? My vision for the future is I would like people, communities, decision makers, I'd like the environmental intelligence I care about to run my business or lead my life. I want it on my smartphone as readily accessible as sports scores are today, with the dexterity for me to choose what do I need and what are my questions, where can I find it? Like I can pick my favorite teams, track my favorite sport, watch the real-time results. Let's get to where that's how pervasively available environmental intelligence is in the world ahead of us. There are promising things on the horizon. We at NOAA are working with our NASA partners and industry partners on various prospects. This is one from the Massachusetts Institute of Technology that might be quite a novel and much smaller way to do the microwave radiometry that we need for atmospheric sounding. It's a good set of microwave optics with a smarter back end electronically. It's showing great promise. But in the CubeSat, even in the mini-sat arena, much less the nanosat arena, Nothing has yet come forward in the way of atmospheric sensors that can live up to the very demanding standards required for modern-day weather forecasting and environmental intelligence. We have to find ways that we can enable this kind of innovation and break through some of those barriers. I've mentioned several times the importance of in situ observations. I want to put a face on a couple of those, literally in the upper right-hand corner there, a face. Satellite data don't stand alone. We're working at NOAA and with our Navy and ocean partners to investigate a number of new platforms that might contribute to getting us the third dimension of our ocean. How do we procure these in large numbers? How do we make them durable in the very harsh and different environment of the ocean? How do we handle the data collection and fusion problem when you're operating in an environment that's not transparent to electromagnetic radiation? You can't beam the data down or up from the undersea like we can beam it down from space. And how do we solve the latency challenge? I love my little seal friend, but wherever he or she goes for a few weeks, that temperature record is not coming back to us for days or weeks afterwards. So how can these data streams get to lower latency and play a greater role in our medium-term environmental intelligence? Products like these that NOAA puts out with our partners on a daily basis, this is a classical coastal environmental intelligence product. These are the layerings of many, many, many of these data streams and analyses and modeling and layers. And this is the kind of product that real-world people are looking to us to provide in their vocabulary, at their scale, about their community, not about our sensor or our science or just the research question. And this is the challenge that really drives the passion in all of the folks who work at NOAA. Sustaining the open data paradigm will be, I think, another challenge, at least in the midterm, or at least in the United States. We are having a dialogue or a debate within our political system about whether to commercialize weather data, to let the satellite and the data be the property of one single company, and instead of governments operating the satellites and sharing the data together, let companies own and operate the satellites and sell the data streams to many governments. We continue to believe strongly in the higher value of the open data model, but we are obliged by our Congress to do some analysis of this other prospect. So we are putting together steps to assess what the implications would be, both economically and internationally in terms of our collaboration and in terms of the global weather and climate enterprise overall. I think this will be a challenging several years on this front, probably for many nations. And I encourage this community to keep your eye on the prize and to look at the examples that have been so instructive in past years, from GPS to land imaging data, and certainly to the more than a century's worth of value that we've all gotten together out of sharing the foundational global measurements of our ocean and our atmosphere that enable the fundamental weather and climate forecasting all of our countries depend upon. We do live on a dynamic and interconnected planet. The data that we've already collected should make it clear to all of us that past is no longer prologue. We're preparing and have to prepare for a much more uncertain future. And to do this, we will certainly need the foresight that can only be provided by environmental intelligence and that can only be provided by satellite observations and our scientific infrastructure. We must sustain the system of systems that currently lets us take the pulse of the planet on a regular basis. We can't do this by ourselves, not any of us alone, no nation, no single agency. Everything we do on a daily basis is dependent on each other. And so in closing, yes, the world needs space. Don't forget that the world needs space to produce the environmental intelligence that is increasingly essential to the viability and perhaps even the very survivability of human society and to human well-being on this planet. The world needs us, the space community. It needs you to develop new, more affordable, resilient systems and approaches to maintaining the Earth observation system of systems that we rely upon to track the pulse of the planet. I believe it needs us as a community to continue the global collaboration and the policies that make data freely and openly accessible. and that we need to work with partners across all sectors of commerce and society to find innovative ways to tackle the ever-growing problem of big data. In sum, the world needs from space, I would argue, almost most of all, the environmental intelligence that people, communities, businesses, and nations need to make wiser choices that can better protect the lives and livelihoods of people around the globe, that can move us towards planetary sustainability. Earth systems know no boundary lines, and so we must reach out across our human-created boundary lines to craft this future together and to help each of our nations and all nations on this planet to tackle the challenges that are posed by the changes we see in the world around us. I appreciate very much the partnership that we have already as the United States and as NOAA with many of you who are in this room, and I look forward to working with you together in the years ahead to be sure that we do continue to bring back from space the foresight that our communities so very much need. Thank you very much.
Thank you very much, Dr. Sullivan. Thank you, Kathy. So we have some great questions that some of you have submitted, and we'll try to get to as many of them as we can. The first question, and some of them, by the way, come from young professionals and students in the audience. It's great to have their perspective, which is usually very clear and to the point. This first one is from one of them, and it is, what are the main challenges that NOAA encounters in terms of global collaboration with other major nations, and what actions is NOAA taking to enhance these collaborations?
It's a great question. I would say one of the key challenges is just the different timings, the different patterns, the different rhythms of the governance and budget systems of different countries. So when we try to do something together, like think about a system of systems in space and maybe share the contributions, you know, you would like to be able to orchestrate that so that the United States would make its contribution in a timely way, and Europe could then make theirs, or Japan could make theirs. But all of our systems work on such different time frames, and the dynamics are so complicated, it's hard to march in step. It's hard to stay in sync with each other. That takes a lot of everybody's effort. It takes a lot of continuous building of the human-to-human relationships, so that if we're having a struggle with a budget or a policy question in the United States, you know, our partners in Japan or in Australia or in Europe, we can look them in the eye and say, honestly, I'm still committed to this purpose. We still see the value of this. I'm having this problem. We're struggling with that. And count that we are still in it together. We are still really trying, and we will stick together getting through the rough patches.
Thank you. We have another question from a young person in the audience. Our young people tend to be very blunt, and I think this is an interesting blunt question. Where there is environmental intelligence, there is also environmental stupidity. How do you deal with people who do not believe in climate change?
Well, you know, NOAA is fundamentally the data agency, so I usually do two things. One, I remind them that the meaning of climate is weather on timescales longer than 2 weeks. So in a sense, if you want to try to not believe in climate change, you have to believe the weather never changes. Everyday experience tells you the weather changes. The statistics of weather over a longer time frame, that's what climate is. The other thing is, look at the data. To say that you don't believe the climate is changing would be like to argue with your doctor when he said, I've taken your pulse and measured your blood pressure, and it was this, and it is this, and it is this. You don't want to believe that, because you're going to get, you know, some lifestyle change instructions from your doctor soon. But data are data. This just is what has been measured. Now, projecting into the future, how might the trends continue or accelerate or change? You know, those kinds of projections, they are models. They are computational models that embody humankind's very best understanding of how this planet works, accumulated over decades. The science of how carbon affects the the radiation and energy balance of our atmosphere is not recent, trendy science. It's 70 years old. It's fundamental physics. All models are wrong. That's a simple truth. But some models are useful. So the same kind of model that tells you Hurricane Sandy is going to miss your community or hit your community, that's pretty much the same kind of model that's telling you what the range of possible outcomes in the future will be. So we focus on the data. We focus on the reality that it's just a question of the dynamic patterns of the Earth on different timescales. And the data show lots of things are changing. Helpfully, I think in the last several years, more and more people, in the United States anyway, more and more people in more and more walks of life, of more and more political philosophies, they're experiencing those changes. You know, they're noticing the ragweed season is longer. They live in New York or somewhere here in Canada, and they notice we don't have a frost. You know, the number of days without frost is getting longer and longer. You know, if you live up north in the northern hemisphere, you like the frost. It kills off all the bad bugs. So people are beginning to see these changes around them, and that's, I think, reinforcing the reality that this is happening.
Thank you. Another question, what is NOAA doing to better understand and more effectively meet the needs of its users?
We do work on that very hard, and we always know there's far more improvement that we should aim to gain. We do a couple of things. Through all of our weather forecast offices, for example, we have a position called Warning Coordination Meteorologist, whose job really is to be that connection point with the communities. We connect principally with the public sector of communities, with emergency managers. In the United States, our model for weather forecasting counts on the private sector, AccuWeather, the Weather Channel, companies like that, to take the basic information we produce and tailor it for a business or tailor it for your smartphone. So NOAA by choice stops short of doing that. But we do want to make sure mayors and governors and emergency managers have the information. It got to them in a timely fashion. They understand what it means. We've, in the last 3 years, made a lot of progress shifting away from talking to ourselves like scientists and writing our forecasts in a way that only a journal editor would love, and writing it in a way that really speaks, you know, not, let me give an example, not to the intensity scale of a tornado, but to the impact you're going to see on the ground, and to using much more vivid language that normal people understand, like this will destroy trailer homes. People in cars are at grave risk. We've come to that by having town halls and meeting with users and folks in the community, because we don't aim just to be technically correct in our forecasts. We actually aim to have the right action taken in communities to protect people. And we do the same in our coastal mission, working hand in glove with coastal zone managers, with infrastructure managers. What is your question? What question are you trying to build an answer to? What information is a barrier preventing you having a better answer? And how can we provide that information to you in the form that you need and in the time frame that you need it?
That's great, thank you. Another question, how did your experience of being an astronaut inform your perspective as the administrator of NOAA?
Yeah, my background in NASA played a strong role in how I came to NOAA and why I came to NOAA. And it's all of the same thing I've been saying through my remarks. I was stunned and awed, like everyone is, at the opportunity to look at the Earth from orbit myself. It's just an amazing experience. It does shift your perspective on a lot of different levels. But one other consequence it had for me as an Earth scientist, which is what my academic training was, I found I was not at all satisfied with just having the pretty picture. Just the fact that I got to see these great sights. And the thought of coming back to Earth and all I could do with my experience would be show people pretty pictures and tell them how cool it was. It wasn't enough for me. I really felt a strong drive, the phrase I have long used, I felt a strong drive to somehow make it matter, to make it connect back to real lives here on Earth and make the perspective that we can have from outer space, whether it's with my eyeball or with a sensor, make that perspective really matter. here on Earth, bring it to life in the lives of other people.
Okay, and another question, coming back to the challenges of NOAA. How can we better translate our data and knowledge into political decisions?
That is really, so the challenge is basically decision support. How can you support the making of decisions? And decisions are always formed on a variety of factors. People just work that way, right? It's partly evidence and data in front of you. It's partly something rational, objective. And it is always partly a set of values and views that you come to the problem with, each person with a somewhat different one, and countries with a different one. So I think we have to understand that simply having, it is not the case that not the case that adding more data will inevitably lead to better decisions. Because decisions affecting society, affecting a business or a government or a community are always mixtures of data and evidence and values and aspirations. So there's no escaping the fact that it is a human and social process to make a decision. And what we aim to do at NOAA is to be in that decision loop with the decision makers, not only bringing data, but they don't need data. They're looking for information. They're looking for some knowledge. They're looking for some ability to know, am I better going this way or that way with my decision? And environmental data will never be able to absolutely say, go that way or go that way. But it can certainly give decision makers a chance to understand the potential consequences of one versus the other. So there's no escaping decision making as a process. There's no escaping it's a social process. And the core of the challenge that we work on at NOAA is how to move data into information, into knowledge, and be sure we're delivering it in a way that actually connects to that decision maker. So, put a point on this. During Hurricane Sandy, we did not just sit at our desks and type the hurricane forecast and hit send. We sent meteorologists who understand the impacts of hurricanes and can translate what a wind speed is going to mean to real tangible terms. We sat them right next to the emergency manager in about 16 counties and cities and national governors' offices while the governor is living this challenge, while the mayor is facing these decisions. We sat right next to them to help make sure they could understand where the data could help them. And they did not have any problem getting to the data they might need.
That's great. Thank you very much. This is a slightly different take on NOAA's role. How is NOAA approaching space weather? And how is space weather being coordinated among the various agencies of the U.S. government?
So NOAA has the national responsibility for predicting space weather events and their consequences in the United States for the civilian sector, and our Defense Department does that for the military part of our world. We work very closely with the research scientists at our National Science Foundation and in NASA, whose job is to study and understand the fundamental processes of the sun and of the transmission and coupling of energy between the sun and the Earth. NASA, of course, has quite a number of research satellites at various Lagrange points in an orbit around the sun. All of those data streams are made available free and open, and our forecasters look at and consult those as well. We funded jointly with both the Science Foundation and NASA the university teams that developed the best current model that actually explicitly accounts for the processes in the sun and the transmission of energy between the sun and the Earth, and explicitly accounts for how that couples into the Earth's ionosphere. So we work really richly woven with the science community and collaboratively to explore which new applications or methods perhaps will give the best advance in forecasting. But just like in a hurricane, in the United States, you will never get a hurricane forecast or warning from anyone but the United States National Hurricane Center, which again is a part of NOAA. NASA studies hurricanes all the time. National Science Foundation studies hurricanes all the time. We pool that knowledge, we pool that insight. But the important thing is when you're talking about public safety, when you're talking about forecasts that a community or an electric utility operator need to act on, we can't have it be 16 voices standing up saying, here's what I think, here's what I think. We need to have the trusted, reliable, assured voice that issues the watch, the warning, the forecast. And for space weather in the United States, that's NOAA.
Great. One last question for you, Kathy. This is from a young PhD student. I assume he's a young PhD student. And he says, why as an ocean scientist did you apply for the NASA Astronaut Corps?
Well, it's actually a little worse than that. I started as a classic rock-pounding geologist and then moved into oceanography because the geology of the seabed fascinated me. I'm not only old enough that I was with Jim in 1985 at IAF, I'm old enough that plate tectonics was sort of new, and figuring out the importance of the deep sea ocean ridges was headline stuff. And I wanted the opportunity to have a look at that geology myself. Why NASA? Well, a couple of reasons. I grew up watching all the early space program events globally, and how can you not be entranced by the grand human adventure of figuring out, can we leave the planet, and how do you keep people alive off the planet? Fascinated by maps and by the Earth from my youngest days. If I succeeded at being selected as an astronaut, I would get to look at the Earth with my own eyes and not have to look at someone else's vacation pictures. Think about that. Think about the prospect of, you can do one of two things. You can spend a week in Paris yourself, or you can look at my pictures of Paris. Which of those do you want, right? So part of it was just that simple, and the reality is it remains a very competitive selection, so probably they were going to say no to almost everyone who applied. And if they said no to me, I had a great career ahead of me in oceanography. It was not a bad thing. But it might just happen they would say yes.
And we're all very, very glad they did. So thank you very much, Kathy. This is a wonderful lecture, very fascinating and stimulating, thought-provoking. Thank you for taking the time for answering the questions, and above all, thank you for joining us here at the IAC in Toronto, and we look forward to seeing you again in one of our future congresses.